Hello everyone, it's Chemicator. Welcome back to my channel. In this episode, I'm gonna break down the total synthesis of pedrolide, a diterpenoid with a unique 55566 free-fused hexacyclic carbon skeleton. Pedrolide first isolated in 2021 from Euphorbia, which is the rich source of diterpenoids. But why its structure is interesting for synthetic chemists? The core structure of this natural product is built from a diterpenoid called pedrolane, in which 6 rings are fused together. In this 3D model, you can see the pattern of the fused ring system. Let's start from the left side of the molecule. Pedrolide has a unique bicyclo 2-to-1 heptane ring, which is formed by 2 fused 5-membered rings. The third 5-membered ring is on the front side of the molecule, fused to a 6-membered ring on the back side. This 4-ring fused system creates a cage-like structure. Another 6-membered ring is attached to this cage system, which is further fused to a 3-membered ring. Additionally, it consists of 12 stereogenic centers. The complex nature of this highly congested skeleton makes it a fascinating target for synthesis. In 2021, the structure and biogenetic pathway of pedrolide were illustrated by Maria Freira's group. According to their proposed pathway, the pedrolane core is derived from ticlian, a diterpenoid with a 576 free tetracyclic ring system. After the installation of functional groups, it is converted into pedrolide. In 2023, Professor Carreira's group achieved the first total synthesis of pedrolide in 20 steps, utilizing a sequence of Diels-Alder reactions to construct the target molecule. In 2024, Professor Chang Li's lab reported a new strategy for synthesizing pedrolide, enabling access to larger quantities of this compound. In this video, I'm gonna explain this strategy. Now let's analyze the retrosynthetic pathway. The target molecule can be generated from this intermediate through several functional group interconversions, including a diesteroselective cyclopropanation. The 6-membered ring in this compound can be formed via a ring-closing metathesis reaction, and the lactone functional group can be introduced through a lactonization reaction from the corresponding alcohol and ester moieties. These two substituents can be achieved via a regioselective epoxide opening reaction. The two key substituents can be installed on the molecule through alpha-alylation and crotylation of the ketone group. This ketone intermediate can be obtained by oxidative cleavage of the parametoxyphenyl group, and the epoxide originates from the diesteroselective epoxidation of the double bond. The bicyclo 2-to-1 heptane ring system can be synthesized through an intramolecular Diels-Alder reaction between cyclopentadiene and olefin with ester substituent. This double bond can be introduced via a Wittig reaction of the corresponding carbonyl compound. Finally, this compound can be obtained through an enantioselective N reaction between cyclopentadiene and trans-parametoxycinnamaldehyde. Now let's go through the forward synthesis. The first step of the synthesis is a one-pot reaction. To simplify, we can break it down into 3 main steps. In the first step, parametoxycinnamaldehyde is installed onto cyclopentadiene in an enantioselective fashion via an N reaction at room temperature. In the second step, the resulting intermediate undergoes a Wittig reaction, transforming the aldehyde into the substituted double bond. In the final step, an intramolecular Diels-Alder reaction occurs between cyclopentadiene and a double bond generated from the Wittig reaction. This step is performed by increasing the temperature to 120 degrees to form the bicyclo 2-to-1 heptane ring system. But it's not as straightforward as it seems. In the first step of the reaction, TMS-protected diphenylprolinol is used as an organocatalyst to induce chirality in the product. The reaction begins with the nucleophilic attack of the prolinol onto the aldehyde, forming an iminoigan intermediate. At this point, cyclopentadiene can act as a nucleophile and produce a desired product. However, it can act also as a diene moiety and trigger an intramolecular Diels-Alder reaction, which competes with the N reaction. According to the reference, the outcome of the reaction is controlled by three factors: the choice of catalyst, additive, and solvent. By choosing methanol as the solvent, TMS protected diphenylprolinol as the chiral catalyst and paranitrophenol as the additive. The reaction is directed toward the desired product instead of the Diels-Alder reaction. Now let's visualize this in 3D to see how chirality is induced. In its transition state, the bulky substituent blocks the back face of the molecule, so the nucleophilic cyclopentadiene approaches from the opposite side. The double bond abstracts a proton from the sp3 carbon atom, leading to the attack of the double bond at this position. Notice that this mechanism creates a 6-member ring transition state, making the reaction easier to perform. After hydrolysis, the substituted cyclopentadiene is produced. But that's not the end of the story. The substituted cyclopentadiene is highly reactive and exhibit dynamic behavior because of the two double bonds confined in a ring with a cis conformation. As a result, it undergoes a rapid 1,5 hydrogen shift, leading to the mixture of products. These types of molecules, which exhibit dynamic behavior, are called fluxional molecules. I've created a video that explores this topic in depth. Check it out if you are interested in fluxional molecules. These two products then undergo Wittig reaction to create the corresponding olefins. Notice that we obtain two Regioisomers product, but the final product is a single diastereomer. What do you think about that? The key factor here is temperature. The mixture of products undergoes rearrangement under heating conditions to form the less stable 5-substituted cyclopentadiene. This intermediate will undergo an intramolecular Diels-Alder reaction to produce a bicyclo 2-to-1 heptane ring system. So the reaction proceeds without need to separate the regioisomers. In the next step, an additional methyl group is introduced into the bicyclic intermediate using LEA as a base and methyl iodide. Notice that during this reaction, the stereochemistry of the ester group is inverted to produce a more stable conformation. In theory, the methyl group could be installed on the ring without this additional step. The desired product could potentially be obtained by using a phosphonium salt with the additional methyl group. However, the authors pointed out using this phosphonium salt failed to produce the desired product. In the next step, this double bond undergoes stereoselective epoxidation with MCPBA, followed by oxidative cleavage of the PMP moiety using ruthenium chloride and sodium periodate. The resulting carboxylic acid is first converted to an alcohol and then oxidized to a ketone via Ley oxidation. Next, the allyl moiety should be installed at the alpha position of the carbonyl group. In the first attempt, the group used KHMDS as a base and allyl iodide in cyclopentyl methyl ether as a solvent, but it resulted in undesired stereochemistry at this carbon atom. However, treating the resulting product with KHMDS led to epimerization, yielding the desired stereochemistry. The others pointed out the enolate of this compound dissolved well in CPME unlike its ketone, and its difference in solubility promotes the epimerization process. Now it's time for crotylation of the ketone group. Using crotyl grignard chloride led to the mixture of products with a 1:2 ratio, differing in the stereochemistry at this carbon atom. Unfortunately, the desired product was the minor isomer. After extensive investigations, it was found that using potassium crotyl trifluoroburate in the presence of boron trifluoroether complex provided the desired stereochemistry. If you are interested in such asymmetric reactions, check out this video for a deep dive into asymmetric synthesis. In the next step, the metathesis reaction proceeds using the second generation of Hoveyda-Grab's catalyst. Following this, intramolecular lactonization and regioselective epoxide opening occur using lithium dimethyl copper, and the resultant alkoxide reacts with benzyl bromide in one pot to provide the KH compound. Notice that the synthesis route yields a large quantity of the compound, confirming the reliability of this approach. The final stage is the installation of the cyclopropane ring onto the compound. Several approaches for constructing the cyclopropane ring were attempted, such as photolysis of cyclic diazine, diphenyl isopropyl sulfonium ylide addition, represented by Wander, and cascade rearrangement developed by the boron group. However, none of these methods were successful in constructing the cyclopropane ring. Ultimately, it was found that this compound would be a stable and effective precursor for the desired cyclopropanation. To access this compound, the double bond of the intermediate undergoes diastereoselective dihydroxylation, followed by selective oxidation of the less hindered hydroxyl group by tempo, all in one pot. Afterward, treatment with KHMDS and HMPA in THF, followed by the addition of the MOMBR protecting group, provides the desired intermediate. Next, the direct cyclopropanation with dimethylcarbene was examined, but no reaction occurred under these conditions. As an alternative approach, treatment with CHBr3 and sodium third butoxide led to the installation of the dibromocyclopropane ring. In the subsequent step, two methyl groups were installed on the cyclopropane ring using lithium, dimethyl copper, and methyl iodide. To complete the synthesis, these two hydroxy groups were deprotected using HCl. Then they underwent selective esterification. According to the previous reports, the hydroxy group adjacent to the cyclopropane ring is more reactive than the other. However, in this case, the opposite hydroxy group was more reactive, making the chemoselective esterification a challenging step. In most cases, esterification of this hydroxy group was dominant, and a double esterification product was not found. After screening several conditions, it was found that slow addition of isobutyryl chloride and triethylamine to a preheated DCM solution resulted in 1:1 ratio of ester products. The undesired product could be separated and treated with potassium carbonate and methanol, allowing regeneration of the diol compound. This diol was suitable for esterification process again without further purification. The desired product was obtained in 77% after 3 cycles. Finally, treatment of this compound with BZOTF and predene gave the desired product. Notice that if this hydroxy group had been esterified first, it would have completely prevented the subsequent esterification of the other hydroxy group due to esteric hindrance. The target molecule was then produced by hydrogenation and removal of the benzyl moiety, followed by DMP oxidation in one pot, giving the pedrolide.